Okay, good morning. Here we are again at the physics video lecture. This is the psci 168 video lecture 6. And today I'm gonna keep it a little shorter and send you off to look at a video that I've put on my playlist. So we're gonna begin by reviewing about forces, and I'll put a couple of interesting problems up here to make sure we've figured out what's going on. So we'll start with the vector nature of force. And we know that forces add like arrows. And what I'm going to do here is just draw one of our scenarios, and I'll put some numbers in. So suppose we have 10 newtons and we have these two scales here. Just like in our demonstration, we know that this 10 newtons here corresponds to 5 and 5. And because the forces add like arrows, these triangles, these geometric triangles also correspond to force triangles. So what that means is, if this is symmetric, I've got 5 newtons here, and what I'm just going to say is I've got 5 newtons and 0.25 meters, and I've got 1 meter. Okay. So there are two triangles here, and they're both the same. They're similar triangles. So I'm just going to label this one with 5 newtons, this with 0.25 meters, and this with 1 meter. And from this, you can find the unknown hypotenuse, and therefore you can also find the tension. So the tension would be the hypotenuse of this triangle right here. So I'm going to call this tension T. Over here, this is 5 newtons. But this triangle is what allows you to figure out what that hypotenuse is. So 0.25, 1, what's the hypotenuse? And then do similar triangles. So I'm going to go here, so find x. And then the second part is find T, the tension. So x will be some number of meters, and T will be the tension in newtons. Okay. So that was the vector nature of force. And we went on to talk about structures, and the vector nature, and these were tensions. Structures had tensions and compressions. So that's the first thing. What we did next was the law of the balance. And I had, for example, a balance suspended here right in the middle, and we could put the small mass here and the large one here, and they would balance. And the law of the balance, we send this up to write it directly underneath. So this is the one side and this is the 2 side. So the law of the balance was that, and this is L1, L2. So the law of the balance was that the force 1 times L1, force 2 times L2. And you can make as many numerical examples as you want. But one thing's pretty clear: if the force is twice as great, the length is going to be half as long. Okay. So you can do examples on these. I gave a little more sophisticated one with the square and the circle, so you can review that as well. The next thing we want to now talk about that builds on this is the law of the lever. Okay, it's going to take us right where we want to go. So for the law of the lever, the demonstration we would always do in class together would be the following. We would just take a board. Okay, so this is a board, and we have a little fulcrum here. So that's terminology. Fulcrum, it's this triangular metal wedge that we have. And we actually stand one of our student colleagues on here, and then we just push down with our hand here, and we can lift, we can lift the person because we have that leverage. Now the law of the lever is going to be just like the law of the balance. So I'll just label it the same way I had labeled. So this is going to be your weight, we'll just call it F sub 1, and this is going to be the distance, L sub 1, to the fulcrum, and then this here we're pushing down with F sub 2, and L sub 2 is going to be the distance to the fulcrum. So in a sense, it's just like the law of the balance because we're just holding it in place. So we have F1 L1 is equal to F2 L2. So what's the difference here? The difference is we can actually not just hold it, but we can push down on this side and lift someone up on the other side. Okay. So this is a fun demo to do when you have live people here, and you can adjust these ratios. You can stand closer or further away from the fulcrum and adjust how much force it takes to lift them. But this is exactly what we would be doing. We'd be lifting or holding up and then lifting our friends and colleagues just by using this board here. So that's the law of the lever, and that's how the demonstration goes. And here's actually an interesting point as well. Just based on, use another color, based on the geometry right here. Let me in fact extend this fulcrum a bit. I'll extend the fulcrum, okay, and I will put a dotted line here. That's, so to speak, our ground level. Now, how much can I lift someone up? If we started here, okay, if we started right here, I can lift them up to about that height. I'm going to draw this in another diagram in a moment. Correspondingly, I can push that, when we'll draw a second picture, but if you take the straight line from here to here, then I started with the board up there. So my point is that I'm going to be pushing this large distance here to lift someone up this small distance over here. Let's do that with a more accurately labeled set of triangles. And this, of course, is the key of how to lift really massive weights, is by using the law of the lever. So we were talking about the construction of all manner of stone structures, and this is how it's done. So, also law of the lever. So let's go ahead and start with a fulcrum, a ground level. This time I'm going to use my ruler. And this will be a real example. Let's not exaggerate things too much. So we'll do a fulcrum about this high. Okay. I'm actually going to use the straight edge here. So since this is an exact meter stick, I can go from here we go, the meter stick, there's that, and I went to there. Okay, so that was my original. Go ahead and do this one in red. Okay, and we're going to press down. I have to keep this length the same, about 20 centimeters, very well. I'm going to press it down to about here. There we go. So here's the amount of lifting I did. Okay. And here's the amount of pressure I exerted. So this again is an example of similar triangles. You know, the small triangle here and this large triangle are similar triangles. Along with the law of the lever, it means that to lift this heavy weight on this side, which was this one here, this short distance, I had to press this longer distance with a smaller force. So we have still F1 L1 equals F2 L2. For balancing the thing, but for lifting the thing, I could give these some new names here. I could have this H1 and this H2, and because of similar triangles, I'm also going to have F1 H1 is equal to F2 H2. And now these are the distances I lifted. So I had a very large force times a small distance equals a small force times a greater distance. And it's just the ratio of these lengths as it was before. So these ratios are going to be the same. Now, there's one thing missing with this law of the lever, and this is just some more geometry. This is really just holding it in balance at this point. It's just like the law of the balance. And it's just a strictly geometrical relation there. If this side is 4 times as long as the right side, then the force is 1/4 the other side. Okay, so those are very basic and simple. There's one thing missing, and that is this. So suppose I balance the ruler right in the middle. Okay, clear enough, balance it on my finger right in the middle. Then all of the weight of the ruler is right here, and I can just do my law of the balance as before. What if I want to do the law of the balance with my ruler right here? Okay. Then, if I let go, it's going to fall. I'm going to have to hang a weight on this side to make it balance at this point. So this is what I'm going to draw up on the board and discuss now. And then I'll send you to watch an interesting video. So what we have to have, and I'm going to keep these numbers going, so 0.5, what we have to have in addition to this is a concept called the center of mass. So because up until now, the weight or the mass of these rulers and boards and whatever we're using didn't play a role, but now they're going to. So 0.5 here, center of mass. I'm going to define it right now. It's just the point at which an object balances. It's the balance point. Okay. And so my first example, I'll just take this ruler. There it is. It's a meter stick. And right there in the middle, as I just demonstrated, is where you can balance it on your finger. And I always like to use a little star for the center of mass. That's just the way I do it. So there we go. We've got the center of mass here. And we can balance it very carefully on the fulcrum. So that's the first point of the center of mass discussion. Now the second thing is this. Well, we'll draw it on this picture here. We know that F sub ruler, let's call it F sub 1 again, is pointing down, and that little fulcrum, of course, is balancing it so that two vectors are opposing each other, okay, the two forces. Again, that's just the weight of it as you feel it in your hand. Now, so F sub 1 is equal to the weight of the ruler. Okay. Now my second picture, I'm going to draw the same ruler and we know that the weight is located right at the center of mass. So that is the center of mass, right? The balance point there. But instead, I'm going to put the fulcrum right here. And obviously, it's just going to fall. It's going to fall down unless I counterbalance by hanging something here. Okay, so there's a block that weighs something. There's a weight right there. Now, here's what we're going to do. We know that the weight acts at the balance point, or weight acts at the center of mass. Let me go ahead and write that down. Weight, which is a force, it's a force of gravity, acts at the center of mass. So if we have F1 here, then we have to balance it with an F2. Now the thing is, you don't see this one here, okay? On my picture, you're just seeing this weight that's hanging here, but guess how I can label this thing? Same as before, L2, L1. So if you include the center of mass, it's still the law of the balance, okay? So now, we still have F1 L1 is equal to F2 times L2. It's the law of the balance, but now this massive object has a force and it acts formally and realistically, it acts at that center of mass point. So this is easy to visualize. You know, I'm balancing the ruler here, but I'm pulling down with something. You know, my finger here, I'm pulling down in order to have that balance. Let's see, the midpoint of that ruler is where this side is pulling down, so I have to balance it. Okay, this is all I'm going to leave you with, because I'll be right here next. I have put in the playlist for this class a short video that shows a man who builds enormous concrete structures just with his own strength, using principles of balance and leverage and center of mass. So there's a video, and you'll find it in the playlist, about Wally Wallington. Guy's name, constructing his own Stonehenge, and you'll be impressed. Wally Wallington and his Stonehenge. It's a short video, but it's really excellent. So let me say something about this. You want to watch this video, and in terms of the homework for the video, just take some good notes about this video, get some screenshots, and what I'm going to do in the next lecture is using these principles, give just a nice sketch of what he's doing, how he's using this leverage principle. Because he's actually lifting with his own strength concrete beams that are, something, what does he say, 19 feet? So he's got a concrete beam that's twice the width of this board. And, very massive. How's he doing that with his own strength? So, in terms of the homework, watch the video. Take notes. Sketches. And I should also say, so notes, sketches, and some screenshots. Print out some screenshots if you find some good ones. Screen captures. I'll just call them screenshots. If you're not able to print these types of things out for your notes, then you just want to make some nice sketches. Okay, if you don't have access to a printer to print them out, I had some students tell me that. That's no problem. So get some nice sketches of that. So I promise you, this is a very interesting discussion, and it's going to lead us right into some further principles. In fact, it's going to lead us finally into the energy principle, which is what this class is supposedly about. Right? We haven't had energy yet, but we're getting there. Okay, so enjoy this. We had a couple problems up here before on the board. So as far as these homework problems go, leave room in your notes and just work them and fill them in. If you're not able to do them, or if you have questions, just send me an email and we'll talk about it, and I can put it in the next lecture. Okay, so some feedback on that is always good. And with that, see you guys next time.